Today, we are going to finish up Chapter 3 and complete Chapter 4, most of it. And then on Thursday will be a really important day where we will cover all of Chapter 5 on the normal curve, or at least most of it. Then next week, Tuesday, will be a review for the exam that's coming up on Wednesday. 1 week from tomorrow is our exam. Did you forget? Doesn't that seem soon? All right, so if we don't finish up Chapter 5, we'll do some of it on next Tuesday. So now, here's where we left off on this page, but I told you that, to learn this on your own. But it turned out in the other class, it seemed like people needed a little help with it. So even though I know you've watched the video and completed homework on it, I think it would help you if I just quickly go through it. And that's what I did with the other class, and it seemed to help. So we already learned how to read a histogram, and now this example is how to draw a histogram. And this is a histogram there's 500 students, and the first step's already done for you. They're broken into intervals. Their GPAs are broken into intervals. All right, so 50 students scored between a 0 and a 2 GPA. So these widths are gonna be on this horizontal axis here. This will be GPA, and it will go from 0 all the way to a 4.0. So here's 1, 2, 3, and 4. And what it's saying, this first interval is really 2 points long here, 2 GPA points long, and it has 50 people. So we change 50 people into a percentage. Remember, the area of each block in a histogram represents what percent of the students lie within that block. And the total area of the entire histogram represents all 100% of the students. So how did we get this? We said, okay, 50 out of the 500 is 10%. So 10% are in this group. So the area of this block is 10%. The width of the interval is what? It goes just from here to here, so we'll call it points. So 2 minus 0, just 2 points wide. And now we want to know how tall to draw it. Well, first of all, let me label this axis. So this is going to go up to 60. Let's do it by 10. So this is 10, 20, 30, 40, 50, and 60. And what the units are here is percent per grade point, of the population per grade point. Okay, so from 0 to 2, that's 2 units long, and we know that inside here is 10%, so we would ask ourselves, 2, the base of the rectangle, times how high should I make it, times what is going to give me an area of 10%. So 2 times what's 10? 5. So that is what we want. 5 right there. So we want it 5 high. 5 high. And that's 2 times, I'm going to draw a 5 here. So 2 times 5 high is 10. Because we know that it's 10%. Another way to do that, obviously, is if you think of this as area, and you think of this as width, well, you know that width times height equals area. Width times height equals area. So height is, just divide both sides by, is area divided by width. So another way to do this would just be, say 10% divided by 2 points, which is equal to 5% per point. That means that 5% is in this point, and 5% is in this point, per unit here, so 10% altogether. All right, next one. Now we're going between 2 and 2.5. 2 and 2.5, just this little interval here. What percent of the people are there? Well, there's 150 people, but remember, we want to know what percent that is, so 150 divided by 500 is 30%. you'd have to multiply, it's 0.3, but then you'd multiply by 100 and you get 30%. So there's 30%. So now 30% of the people are in this interval. So we have to say, all right, this is a half a point wide, isn't it? 2.5 minus 2, so that's 0.5, that's the width of it. This is the area. So the width times what is going to give us that? 0.5 times what will give us 30? Half of what is 30? Half of what is 30? Half of what is 30? 60. Half of 60 is 30. Okay, so we want to go up 60 high. That's what we want to do. And there it's 60. Or you could just say, okay, the same thing, 30% divided by 0.5 points is 60% per point. Same thing. Okay, and we can do that for everything. Let's just continue on. So here we have 250 out of the 500, which is obviously 50%. Probably it's a good idea to do all this whole column first. Why? 50 out of 500 is 10%. Because then you can check to make sure that you didn't make a careless error, because all these should add up to, obviously should add up to what? 100%, because it represents 100% of the histogram. And it does. We did it right. All right, so we'll do the next one. And the next one goes from 2.5 to 3.5. So what's the width of this interval? We're just taking the width of this interval. What is it? It is what? 3.5 minus 2.5, it's 1 point long. So 1, this is an easy one. 1, and in the area we know is 50%, so we're saying 1 times what is 50? 1 times how high is 50? 50. So we just want to go up to 50. Okay, so that's 1 point, and 50 divided by 1 is 50% per point. And then our last one is, we just have another little half of a point here, just a half a point wide. So we're going to put a 0.5 points there, and then we'll say 0.5 times what gives us 10%. So we want 10% in here. So we'll say half of what is 10%? A half of 20 is 10%. Whoops, I made it up to 30. Sorry so much. We want it just to here. That's 20. I really confused you. I wish I had whiteout. This is 10%, and this height here is 20% per point. So just put a little 20 over there. And all I did was I said, okay, the area divided by the width. 10 divided by half is 20. All right, percent per point. And you might want to eyeball it and say, does this look right? These should be the same area, are they? Well, this is 1, 2, 3, 4 blocks, and this is 1, 2, 3, 4, yeah. So you should just look and see that it makes sense. All right, any questions on that? Okay, so let's just answer these two questions here. It says the interval between this interval has the most people, half the people are in this interval. Is it the tallest? No, it's not the tallest, but it does have the greatest area. It does have the greatest area. Questions on that? Okay. There was two things we didn't do last time, so I just want you to turn back to page 22. And these are two questions that we didn't really go over. So I just want to make sure you understand these. The first question says, this was a histogram of the final exam scores of a group of students. And my question is this. It says, if you added, let's look at the histogram here. There it is. If you added 10 points to everybody's score, let's say I wanted to add a 10, so that the highest you could get would be 110. And the lowest, the person who got a 0 would go up to 10. So if you added 10 points to everybody's score, would the histogram change? How would it change? Do you think it would change? Would the shape of the histogram change? Wouldn't you just like lift it up and just shift it over 10 points? Does everybody see that? Same if I subtracted it. If I subtract or add a constant to everybody's score, the shape wouldn't change, the spread wouldn't change, but would the average go up? Would it? Would the middle number go up? The median? They would all go up, but the overall shape wouldn't. The spread wouldn't. The numbers would go, here they go, there's a spread of 100. If they went up 10 points, it would still be a spread of 100. It would just go from 110 to 10. So that's an important visual that we're going to look at, I want you to think about later on in a few pages. Now there's one other question here, and it said, what percent scored exactly 73? Well, we know the whole block scored 25% because we said the area of this whole rectangle is 25. But how do we know what, for example, somebody who was 73 scored? Well, if you assume this is all evenly distributed through here, 73 is just 1 unit long. And you know what this height tells you? It tells you the percent per point. It's saying that 2.5% scored 71, 2.5% scored 72, 2.5% scored 73. And since there's 10 of those units in here, that's where we get the 25%. So if I asked you what percent scored 54, what would be your answer looking up there? What? 1. What if I said 54 or 55? Both of those, 54 or 55. It would be 2, because 1 for 54 and 1 for 55. And what if I said, between 50 and 55? That would be half the block. So you could either say, 1 plus 5 of those, or you could just think 10 divided by 2. You'd get 5%. All right, I think you understand that. Now, we don't have much to do left in this chapter. So I'm trying to think about what the best way to cover this is. And sometimes, what I say here is that the vertical axis sometimes will not be labeled in a histogram because although in every other graph you've ever seen, you know how important it is to label both axes. Well, here with the histogram, since you know the whole thing has to add up to 100%, then the labeling the axes can be redundant. We could change that. We could figure out the heights, knowing the percentages, and knowing the horizontal axis. So if you don't see, that's why sometimes you will not see the height labeled on histograms. It won't change the shape at all. All right, now the number of intervals, that's something that we'll talk about in a minute, but first let's do this problem. Sometimes a rough sketch of a histogram can give you an idea of the general distribution of a set of data. So it's often you'll see just a rough sketch of a histogram instead of the exact blocks, the rectangular blocks, just a general sketch of it. So for example, let's look at these 3 histograms. And they show exam scores from 3 different classes here. 3 different classes. So just looking at the shape of these histograms, it says which class has the highest percentage of students scoring over 50. I just want to get my highlighter here. Scoring over 50. So you can just eyeball these, and just the general shape would tell you. We'll make a line at 50, and we're looking at this area right here, over 50, for this group of students who took an exam. And then for these 2 groups, The percentage is represented by the area, so we're looking at that area and this area. So the first question says, which class had the highest percentage of students scoring over 50? Which one do you think? Just shout it out. A. And how about for, which one had the lowest? B. Even though, and which one had about the same? C. Now it says, which class had two distinct groups of students, one doing very well and one doing quite poorly? B. You know, this is an example of an exam, let's say, where you've probably taken examples like this where the majority of the class does poorly, flunks. They probably scale them. But then there's always this group, not always, but sometimes, that do incredibly well. So I don't give exams like that. I deliberately wouldn't want to give an exam in a gen ed course like that. You might give an exam like that if you wanted to identify the super brilliant people in a course and didn't care about the rest of the class. All right, now I said that I would show you how the number of intervals can affect how you decide on how many intervals you want in a histogram and how the histogram changes. Let's look at our own data, okay? So let's go to the PC, and there is no mouse. Hold on, it's over here. Okay. So this is the survey that you guys filled out. And remember these questions? So they're displayed here. And for example, we can look at how many pairs of shoes do you own. So let's click on histogram for that. Shoe number. And now you can adjust how many class intervals or bins there are by doing this. For example, if you do this, what does it tell you? It tells you, I'll show the statistics here too, it tells you that people in our class ranged from having one pair of shoes to having 100 pairs of shoes. And that represents 100% of the data. Not much information there. And then you could go all the way to the other extreme, and now you see there's 100 different class intervals. And so this is sort of like a bar graph, except these numbers don't tell you how many people are in each interval, they tell you the percent. So for example, what is this giant spike above 20? This tells us that what percent, the area of this stick tells us what percent of the class answered 20 pairs of shoes. So how would we figure that out? Well, the base of this is just 1 unit long, just for the 20. You wouldn't go 20 minus 20 is 0. It does have a width there. You could think of it as between 19.5 and 20.5. It has a width of 1. And what is this? That doesn't mean 12 people. That means that's 12% per shoe, per pair of shoes. So that means that 12 or 11, about 11% of the people answered 20 pairs of shoes. And what happened here? 19 pairs of shoes. That's only what? 1% or even 0.5% answered. Very few. Looks like 0.5% had 19. What are these spikes? Look at these spikes of people. This is what? 10. No, this is 5, 10, 15. No, 20 is here. This is 10. So this is 5, 10, 15, 20. This is 25 or 30. 25, 30, 35, 40. That's 50. Whoa. Do you think people just buy shoes like that? Once you hit a 5, once you get to a round number, you say, oh, not buying any more shoes. Or when you get to 19, you say, oh, I gotta get that 20th pair of shoe. Why are we seeing this? Do you think if you guys went home and actually counted the shoes in your closet, it would look like this? Do you think hardly anybody would have 19 and so many of you so many more people would have 20, exactly 20? Why do you think we get this? Anybody? Yeah? Yeah, I asked you. You didn't go into your closet and count up your shoes, probably. I asked you to ask, and you probably just estimated. And when people estimate, they estimate with these round numbers ending in 0 or 5. So that's something to watch out for, that people's survey responses aren't necessarily, they're going to differ from what the reality is of actually how many pairs of shoes they own. Okay, so we might not want so many bins like that with all those spikes. We might want to just get a general idea, more or less like that. You can see here that, there aren't many people who have over 50 shoes, right? And if we actually clicked on the statistics, it says that the average is 15, and the median is less than that. The middle person has 12 pairs of shoes, but the average is brought up by these extreme people over here. And now you might want to think, how would the graphs of males and females differ? I wish that hadn't been labeled, so you'd have to guess which was who. But it's already labeled, so you can see that the males are there on the top graph, the females are on the bottom. And don't they look quite different? And if you look at the statistics, it will show you they're quite different. The average for the guys is what? 6.883, and the average for the girls is almost 20. The middle girl has 17 pairs of shoes, the middle guy has 6. There is a guy with 7, who's he? 77, doesn't say. When you click on it, sometimes it just gives a number. It doesn't ever say your name, but it doesn't give a number. So there is somebody who has 77 pairs of shoes, and then there's a bunch up here who have 100, and oh, good. Everybody has at least 1 pair, and the girls have at least 2. Wouldn't that be sad if somebody here was shoeless in this weather? I would bring in some shoes for that person. Okay. So that's sort of the idea. And you can look at other, anybody else want to look at anything else before we move on? But you can see how the general shape of the histogram. What is this big spike up here? The guys, there's a whole lot of guys between what? It looks like about 5 to 10 pairs of shoes. Whereas girls, have there's a lot of girls around 25 pairs of shoes. Yeah?
Can we see something that shows the difference between people who have no siblings?
Okay, people who want to look at the siblings? In conjunction with, so what do you want to look at it in conjunction with? All right, shoes? We could look at it with shoes. All right, if we maybe people have a lot of brothers and sisters don't have many shoes. Why don't we try it out? So we'll go back to the shoes. We'll do it. This is how you would do it. You would unclick this, okay? And now shoe number. Okay, so now we're going to split on siblings. And let's come up with a hypothesis. The hypothesis would be what? If you have a whole lot of brothers and sisters, maybe your parents don't afford to, is that what you think? You wouldn't have as many shoes? Should we see if that's true? Okay, so we could split it at how many? 5 or more siblings right here? That would be 5 or more siblings. Or 4 siblings? We could split it, this won't move. I could split it right there. And then we can do the split plot. And here we have level 1, and here we have level 2. Here's the stats, and we can look at it. So let's look at the stats. Show statistics. Hardly any difference. See? These are the people who have more siblings, 49 of them. Actually, their median's bigger, so our hypothesis was wrong. That's how you do it. Cool? All right, any other questions? Okay, so we could look at speed, or you want to move on? We need to move on, don't we? Love? You want to see love? How about love? Let's look at love. All right, no, not like that. Let's unsplit it and let's show you 7 bins because there were 7 possibilities. Oh, these are the people who said no one. There's not anybody in the whole wide world for them. Oh, well, we can be assured that there aren't that many of them. That's 1 unit. There aren't. There's only like 1%, thank goodness. On the other hand, let's look at the people who said, and this is how we coded it, this was no one. How many people in this world could you truly love? This was no one. This was just 1. I know. This was 1. This was a few. We're coding it as 2, but we said it's really a few. I just coded it as 2. This I said was dozens. I coded 3 as dozens. This is hundreds, thousands, and millions. Well, look at the millions. They're so optimistic. Isn't that cheerful? I mean, they're going to think about it. That one didn't work out. Oh, millions more. Think what a happy attitude you'd have. Okay, so those guys, very positive. And so that's what it looks like. And now if we wanted to say, well, what % of the class answered a few? Well, this is just 1 unit long. So we'd say 1 unit all the way up to almost 50%. That's how you would read that. And if you wanted to see the difference between males and females, you would just click on the split plot here. And what difference do you see? They're a little more optimistic. The guys really think there could be millions of women out there for them. And certainly, look at this, thousands. Yes, compared to the women, didn't think thousands. Yeah. So that's how you can look at these histograms and compare them. All right, so now we're going to move on. And we can look at these again more and have homework problems and exam problems based on our surveys, and a new survey is coming up. First Friday of every month. So let's go back to the document camera. And, all right, now, types of variables. Okay, first of all, a variable is like is any of the answers to our survey questions. They vary from person to person, so they're a variable. Like how many pairs of shoes do you own is a variable. Some of you own, it varies from person to person. So you can classify variables into 2 main types. Ones that basically you answer with a number, like how many pairs of shoes do you own? And one that you would answer with a quality. Like, what's the most important thing you're looking for in a man? Maybe honesty, or maybe a sense of humor, or maybe money. But those are all qualities about the person, categories. All right, that would be a categorical or a qualitative variable in general. So, quantitative variables are best depicted with histograms because we saw that the horizontal axis of a histogram is actually drawn to scale. It pays attention to the numbers. Where on a bar graph, the x-axis is not drawn to scale and is better suited for categorical or qualitative data. That's what I say here. Now, these are examples of qualitative or categorical data. I don't know what you could say it either way. People use those 2 terms interchangeably. And quantitative data is often broken down further into 2 types: continuous variables and discrete ones. Continuous variables are ones where you could measure them with smaller and smaller intervals. Get your intervals tight, just limited by the accuracy of your measurement. For example, with weight, you could measure in pounds, but you could also have a scale that went into smaller and smaller and smaller intervals. And so it's continuous. You know, your weight could be given as 140.3267 is as accurate as your scale is, as opposed to discrete variables where they're usually measured with a whole number. Family size, number of cars owned. You don't need more accurate measuring sticks to measure your family size. It's just discrete numbers. Any questions on that? Oh, okay. Now, so let's just categorize these. What type are the following? Occupation would be what? Qualitative or categorical. The number of pets owned would be what? Quantitative. And furthermore, it wouldn't only be quantitative, it would be what? Discrete. Exactly. How about the region of residence? Qualitative, yeah. And height is, oh, you can't even see, guys. Sorry. And your height would be quantitative, and it would be what? Continuous. Now, these two, think about them carefully. Zip codes. You do answer with a number, but think about it a little bit. Do you think it's quantitative? Raise your hand if you think it's quantitative. You are answering with a number. Raise your hand if you think it's qualitative. Okay. Why is it, we did answer with a number, why isn't it quantitative? Anybody want to explain? Yeah?
Why is it a quantitative?
Why, yeah, because we answered with a number. I'll take the, so.
I mean, because if we could describe age and weight as quantitative, we should be able to describe zip code.
Oh, you think it should be quantitative? You think it should be quantitative? Well, with age, when I tell you how old I am, that tells you how many years I've lived. It tells you, it actually, and it means that I've lived more years than, but when I tell you a zip code, does it really tell you, couldn't that number just be replaced with some symbol?
Yeah, you're right.
Yeah, so that's why it's qualitative. It's just a description of a category. We don't really, that number is just a name for a particular category. It doesn't mean that if you live in one zip code that's twice the number of the other, that you're twice as big or something, or your city's twice as big. It doesn't correspond to any real quantity. Okay, so does everybody understand that? Okay, so this is qualitative, it's just categories. And how about social security numbers? Qualitative, raise your hand if you think it's qualitative. Yes, for the same reason. If you have a low one, like I do, 0, 0, really low, that doesn't mean that I'm smaller or younger or slower or anything, I hope. Okay, now, I think we are all done. Now these summaries are really important, and I want you to read them all for the exam, especially in preparation for the exam, so you know what's in each chapter. Now, on chapter 4 is the average, the median, and the standard deviation. It also talks about the median. And these are numerical summaries of data as opposed to a histogram, which is a pictorial or graphical summary of the data. So these are even more drastic summaries. We're condensing all the data into a single number, an average. Not even presenting a picture when you give the average. Okay, so I think you all know how to compute an average. You add up all the numbers and divide by however many there are. So it's also called the mean. Those two words are used interchangeably. So here's an example. To find the average of a set of numbers, there's 7 numbers here, you add them all up and divide by 7. All right, and we get 20. Now, a median is also a measure of the center of the distribution, but it's different. What you do, to find a median, you first list the numbers from the smallest to the largest. List the numbers from the smallest to the largest. And so you rearrange them. Make sure, so many people on the exam make this mistake. They always put 0 first, thinking it's the smallest. Please. Yep, pretend they're on a number line. This is the furthest to the left. And then you find the middle number. Well, if there's an odd number, there is a middle number. It's right there, and that's your median. Now, if you have an even number of data points, like here, you have an even number Well, we've arranged them in order, and there's 3 on this side and 3 on that side, so the middle number would be in between the 6 and the 10. So what do you think we do? We just go halfway in between 6 and 10, which is taking their average, take the midpoint there, the average, which would be 8, and that will be your median. So that's the only time that a median wouldn't actually be a number on the list, is if it's halfway between 2 of the numbers. So a median's always a number on the list or halfway in between 2 of them. So 8 is the median. All right, now let's move on. And now we're here on okay, so now we're here on page 28. And the question is, find the average and the median of this list of numbers. Okay, so to find the average, that's pretty simple. We're just going to add them all up, and we get 3 minus 10. So we get -7 divided by 7, -1, correct? Yeah? Now, is the median something different or not? Let's see. To get the median, we can't, do we have to rearrange these numbers? The smallest aren't coming first here. So we have to start with the -5, and then the next -5, then the 3 zeros, then a 1, and then a 2. And now there's 7 numbers. The middle number is right there. So the median is 0. Okay. That is our median. And they're not the same. They can be the same, but they don't have to be the same. Now the question is, remember, this is very similar to what I asked you before when I showed you that graph and I said, imagine adding 10 points to everybody's score. We all saw how the graph would just shift up and the shape would remain the same, but that the average would move up by 10 points and so would the median. So this is just another example of that. If you added 5 to each number on this list, every number on this list, well then wouldn't the average go up by 5? Doesn't it just, it's common sense, you can actually calculate it, but isn't it just common sense that the average would go up and the median both? Wouldn't they just go up? Yeah. So they would both increase by 5. Oh, shh. They would both increase by 5. Sorry. I don't want it to get under the computer here. That's just water. Don't slip when you step by here. I'm probably going to slip more than anybody else. Okay. Yeah. You know, if each and every number gets increased by 5, then the average is going to go up by 5. If you have a set of exam scores and I raised added 2 points to everybody, then the average would go up by 2 and the middle person would go up by 2. Is there anything mysterious there? Don't make it more complicated than it is. It's really simple. All right, so 5 is added to each. If any constant is added to every single number, it would increase by, the average and the median would both increase by that. So they would both increase by 5. If you want to do it, you can do it and calculate it. Now, if each number on the list is doubled, what's the new average and what's the new median? What would common sense tell you? If you double everybody's score, double everything, wouldn't you think the average would double and the median would double? And it does. Okay, if each number, and if it turns out to be 0, well, doubling 0 is still 0. So it really does double. You could say it doubles. If each number on the list is doubled, like here, if I doubled each number on the list, well, I'd double the median. Well, it would still be 0, but that's doubling it. And if it was anything else, it would double. Okay, so let's just do this. So if each number on the list is doubled, so both would double. You know, if you're a little bit, unsure of this and you have a lot of numbers and you don't feel like calculating them, what I would always do is just try taking the simplest example and see how it works with a simple example. So I would just say, okay, let's just take the, hey, I'm not sure about this. Let's say it was an exam. I just wanted to check, and I didn't feel like working with a long list of numbers. I'd say, oh, 1, 2, 3. Now, if I double them, double those numbers, what would I get? What would 1 double? 2 doubled. 3 doubled. Yeah. And this was the old average and the old median. And what's our new average? 4. And our new median. And if we added them all together, we would get 12 divided by 3 is 4. 12 divided by 3 is 4. And here you get 6 divided by 3 is 2. So just do that on a, that's what I would always do on any exam, where it's just, hey, just take a simple example, let's see what the pattern is. I mean, it's not proving it, but just reminding yourself of the rule. Okay, questions? Now, let's see if you added 21 to only the top number. So you changed, what are our numbers here? Let's list them again. These are our numbers, -5, I'll list them from the smallest to the biggest. And what do they want me to do here? Add 21 to this. So they want to change this to what? Change that to what? Add 21 to it, so what will it change to? Yeah, so you want to change the 2 to what? 23. That would be way out on the number line. But I'll stick it way out here. It's not very far out. Now, what happens to the median? The median before was 0. And all I've done is taken this 2 and changed it to a 23. I could have changed it to a 23,000. Would it have made any difference? The middle number is still right here. Pays no attention to that. That could be 23 billion. Makes no difference to the middle number. So the median is still 0, correct? That's very unlike the average. If you change any number, increase any number, the average will increase. If you decrease any number, the average will decrease. Doesn't matter which number it is. The average is you put all the money together and divide by how many people there are, how many numbers there are. So if you add even a penny to the pot, it's going to slightly increase your average. And if you add billions, it's going to hugely increase your average. So the average pays attention to all the numbers, whereas the median only pays attention to the order the numbers are lined up in. It's just like a place. It's a middle place. It doesn't look at how far the people are out there or how far the people are out there. They can change their positions. It would only change if somebody crossed the middle and then change, let's say I was the middle and a bunch of people crossed, and then they might become the middle. Then it would change. But if they just arrange themselves any way they want on that side of me or on this side, I'll still be the middle. Okay, so if you add 21 to only the top number, what happens to the average? Well, what was our old sum? Anyway, we had -7. That was our old over 7. And now what are we doing? We're adding, this is what we had before, right? We're way up here. Now, that's what we had before, and now it says add 21 more. Doesn't matter if we just add it, we're just going to stick 21 in here. So we'll add 21 to our pot. Doesn't matter which number it's going to. It's just 21 more into our pot. And then our average goes up to 2. Okay? For example, if we were thinking about the median amount of money you had in your pocket right now, and the median and the average amount of money you guys have in your pocket right now. Those could be two very different things. Very different. Imagine there's a few people in this class, suppose, who have thousands, maybe even $100,000 in their pocket. Maybe a drug dealer. Maybe a gambler, one of us. Just maybe an operator of some sort. Well, that would shoot up our average. The average would be like if everybody had to empty their pockets, and then we divided it up equally, all among you. You'd each get the average. Now, the median doesn't pay attention to that person there. The median's just if you lined up in order from all those who have nothing in your pockets, which is probably quite a few of you, all the way down to that guy, that drug dealer, and whoever is that middle person is the median. It doesn't matter how far that drug dealer is out there, with how many, or gambler, how much his pockets are stuffed, yeah?
How is the top number -7? Like, is it?
The top numbers are not -7. The top number was our previous, I'm just figuring out the average. We'd added up all our numbers before, and we said, the question is, here's our numbers. And our top number was 2. We added all these up and we got -7. Our top number was 2. Now, we're changing that to a 23, which is 21 more. So I take that, -7 plus 21 more. Does that make sense? Yeah?
Why don't we use -1 instead of -7? That's the average. We're talking about the average.
Yeah, I did. This is -1 right here. I could have done that and broken up the fraction and said -1 plus 3 more is 2.
So either way is fine.
Either way is fine, yeah. You could have split the fraction that way. Any other questions? Okay, let's turn the page. And, okay, now we might need to skip this problem for now. Would that be okay, guys? And because it seems like we're running a little behind, and move on. And this will be online, so you can see it online. We'll skip for now. Maybe we'll get back to it. It's a good problem. Skip for now. Now, let's move on. What I want to do is show you how the average, the median, and and what else? Well, that's all. How the average, the median, and the histogram fit together. Okay, well, the median, as I say here, divides the histogram exactly into 2 equal pieces by area. 50% of, remember, area represents the percentage of data. So 50% of the people are on one side and 50% of the areas on the other. If they're people, the middle person is the median. The middle person would divide the histogram into 2 equal pieces by area. Now, the average is where the histogram balances. And I have a nice little visual of that I can show you that might help. So if you go to the PC, and you can see it yourselves if you want, if you went to Stat 100 and then to my lectures, which are right there, and here, went here, and just, okay. So the average and median on a histogram. So pretend this is a histogram, like a number line, and we just have 2 numbers, 0 and 10, all right? So I made a little block indicating 1 number over 0 and 1 number over 10. Now, what would be the median? Right in between the 2 of them, which would be 5. And what would be the average? Well, 10 plus 0 is 10, divided by 2 is 5. They'd be the same. Okay, and that is a symmetrical, and it's where the average is where the histogram balances, like a seesaw. All right, now let's say I add a block right here at 2. Now, what is the median? Median, I have 3 numbers, 0, 2, and 10. So what, the median's the middle number, so isn't it 2? And you see how if I put it right at 2, Do you see how and slice this block right through the middle? Do you see how it divides the histogram into two equal parts by area? You have a block and a half on each side. 50% of the area is on each side. Now, that's the middle number, but what is the average of those three numbers? Well, we have a 0, a 2, and a 10. So let's add them up to get 12. Three numbers. So we have 12 divided by 3. So what's our average? 4. Okay, so 4. It's bigger than this median. It's getting pulled towards this extreme value, and you can think of it as the fulcrum, where the seesaw balances. Whoops, it should have balanced there. Hold on. Right at 4. See? It takes into account the average, how far away that is. It takes into account how far away that is. Does that make sense to everybody? So, for example, here, let me show you. And you can play around with this. You can add and subtract blocks, and you can figure out what the median is, what the average is, etc. Now, with this one, pretend these are homework scores. They are from when we used to call it a lab for a previous Stat 100 class. And they say the median score is 84. The middle person tended to get 84. And there it is, 84. And the lower values, you see the extreme values? The lower values are farther from the median than the top values. We're cut off at 100 here. So you can't get much further. So this is true of just about all my scores, my exam scores and everything, have what's called a long left-hand tail. Because if the middle person does pretty well up here, well, there's a lot more room you can do poorly in. And so they're more extreme. They're further away from where most of the data is. So where do you think the average is going to be? Do you think if I want to balance this, I'll go this direction? Or do you think I'll go towards those extreme values? Can you tell? Watch. I bet it's going to balance always. The average will go more towards the extreme values. So can I get that? See? That's where it balances. And the average is 81.78. It's less than the median because it's being pulled down towards that tail of the distribution, the extreme values. As opposed to, let's go to the next example, this example, which is data on the 42 tallest buildings in Chicago before they built the Trump Tower and a few other ones. So this is the old Sears and John Hancock, I bet, up there. And it's by stories, how many stories they have. Now the middle building has 45 stories at the time. Now of course there's some bigger buildings, but this was a few years back. And now, do you see that the taller buildings, these tend to be farther from the median than the shorter ones? You see? This is also how it is with income, because you can get really rich people up here. So now, if you want to balance the histogram, don't you think the average is going to move towards that tail? They're weighted way down. They're weighting that seesaw down. So let's see where it would balance. Right there at 50.34. The average is greater than the median. The median has divided all these into two equal parts, but the average pays attention to the spacings, and it moves in the direction of, if you're further out on the seesaw, it's going to move in that direction to balance things. Okay. Any questions on that? And you can play with that on your own. That's on your web, just online. Okay, so let's go back to the document camera. And if you want to see what these look like as histograms, draw our own little ones. They're not seesaws, but maybe you can get a little feel for what it looks like without, what happens. All right, so here in example 3, we found the median and the averages of these two numbers. Before we added the 21 is right here. Before we added the 21, what did it look like? Well, we have 2 -5s, so we'll put them there on the histogram. We had 3 zeros, so we'll put them here. We had 1, 1, and 1, 2. Okay? That's what it looked like. And we said that our median is right here. And remember what we said our average was? It was -1. So the average was right there at -1. That's what happened. Now, when we take this, so that's sort of like the balancing point. But if we take this 2 and shift it all the way over to 23, we'll draw a new histogram. That's what we're doing here. We're taking the 2 and putting it all the way at 23 over there. Do you see how it's going to move this average? The balancing point's going to be different. Right now, the average is, these are the extreme values. So the average is to the left of the median. But once we put this way down here, everything else remains the same. This remains the same. This remains the same. And these 2 remains the same. And we just bring this, oh, I'm so sorry. This one, this 2 is no longer there. I don't have white out, but it shouldn't be there. We took that 2 and we pulled it all the way over here. Now, the median's the same because it's the area. We have 1, 2 blocks on this side and 2 blocks on that side. So that's still the middle number. The median's still the same, but when we took this 2 and pulled it all the way over here, we changed the average from here all the way up to the new average. We said, we computed it. We said it was 2. So that would be our new average. And it's pulled in the direction of this extreme value. Do you see what I'm saying? Does that make sense? All right. It's not as pretty as the fulcrum online. All right, now let's move on. And so this is what I'm talking about here with the, in general, I apologize for this being all crooked all the time. It's because, you see how this document camera I have is? This is crazy. It's at an angle and I can't push it any other way. So as soon as we get that fixed, I won't be making you dizzy so much by making these, gets me dizzy working at an angle like here. We're trying to get that fixed. I'll try to keep looking up there and try to make it nice. All right, so now these are sort of just prototypes of what we've talked about. There's the symmetrical distribution. Let's start with that. If the histogram is symmetrical, then how do you think the average and median compare? What would you guess? Fill it in lightly and see if you're right. Okay, what'd you fill in? Equal. That is correct. They'll just be equal, the same thing. But what if we're in this situation where most of the data is here, but then what's going to happen to the average? These are extreme values here. So do you think the average is going to get, remember the average gets pulled towards them. So how do you think they would compare? Greater than or less than the median? Great. If it started off here, the average were mostly, it's going to get pulled towards those data. The average and the median are about the same, but then look, all these extreme values, isn't it going to get pulled towards there? Wouldn't it? What this means here is that, like if the middle data is here, these aren't extreme very far away, these data, but these are really far away. This would be like income maybe, where most people make what? Oh, I don't know, maybe $50,000 or something. Some people make 0. And then there's some people who make a whole lot of money. That's going to make the average go up. So it's greater. It gets pulled towards the tail. Does that help? All right. And then this one, if it has a long, like in our, this is like our exam scores. Most people do really well. And our median is really good, pretty high, like in the high 80s, sometimes even 90. But then there's some people way down here who don't show up to class, just get 20 zeros, just don't even come 0. That's going to pull our average down, so it's less than. Okay? Questions on that? All right. Now, I think we're going to skip this for now. This is just thinking about data sets in the US and how they would be for now, and just because we have a lot to do, so we'll skip for now. And then, when I say skip for now, we'll see if we have time later or not, and I'll let you know. Okay. I'll let you know if you have to fill it in online or if we're going to do it in class. You don't really need that for the homework. Okay, now finally, in the last 20 minutes, we're going to talk about something called the standard deviation. The standard deviation, so far we've talked about the median and the average, and that's a measure of the center of a distribution. What the standard deviation does is talk about the spread of the distribution. It talks about not just what the smallest number is and what the largest number is, that's the range, but it takes into account every single number in a histogram or on a list and looks at how far away it is from the average. So it takes into account the spacing of every number on the list, and it's a measure of the basic range of how much the numbers typically range from the average, deviate from the average, the standard typical deviation from the average, how much they diverge, are different than the average, deviate from the average. Okay, so which of these two distributions has a smaller standard deviation, and why? Notice they both have averages of 0. They both have a similar range from the smallest to the largest, but which ones have smaller deviations? Where are most of the numbers clustered more around 0? In distribution 1 or 2? Just answer. 1, very good. 1. Why? Because you see that there are more numbers that have small deviations that are very clustered around 0. Okay, so this has a smaller SD because the numbers are don't deviate as much from 0. They're not spread out around 0. They're more bunched around the average. That says bunched. They're more bunched around the average. Whereas here, they're more spread out. Here, they're more spread out around the average, so they have a larger standard deviation. They have the same area, it's just here. Imagine if all the numbers were 0. Well, then they'd all be right at 0. There'd be just one stick above 0, one little bar. And here they're more spread out. Okay, now this next one, let's look at these two lists of numbers. And what you'll notice about these, if you add these up, you'll get the same average of 1 for both of them. You can do it and you'll see they both have the same average. But if you draw the histogram of them, which one has the bigger standard deviation? This one or this first or second? They're so much more spread out. This has a much bigger standard deviation, even though the average is the same. This one, it's hard to read. These are all at -9, because there's a whole bunch of them. These are at 1, these are at 11, and this one is at 21. And these are at 1, 0, 1, 2, and 3. They're much more bunched together. They have the same average, but this one has a much bigger standard deviation. Now, how would you find the typical deviation for both of these? We know this one's bigger, but let's calculate how you would find the standard deviation for both of these. And I know that many of you already know how to do this, but the idea is, first of all, we need to follow, let's look at these steps. We want to find out how spread out the numbers are around the average. So our first step is we've got to find the average of each list, right? To find out how spread out they are about the average, we should find the average of each list. Okay, so let's do that. So let's start with list 1. And we already did this. We add them all up and we get 10, right? Divide by 10, and that gives us 1. Now let's do the same thing here. I'm just following this first step. This is just finding the average. So what do I get? Negative 36 here. And what is all this added together? What do we have? 21, 42, 43, 44, 45, 46. Right? Isn't that right? Yeah. So that's 46 minus 36 over 10, and I still get 10 over 10. So they have the same averages, like I told you before. All right. Now we move to so now we know the average, and what we're looking for is we want to find all the deviations from the average. What does that mean? We want to find each one of these numbers. We want to see how much it deviates from the average. This deviates, how far away it is from the average. Well, it's 1 below the average. This doesn't deviate at all. So for each one, we subtract the average from each number. So we say 0, subtract the average is negative 1. And you can see this is below the average, and that's why the negative sign is here. This one's the same, negative 1, negative 1, negative 1. Now we subtract the average and we get 3 zeros, and that makes sense because the ones that are the average. They don't deviate at all from the average. Now, 2 is 1 above the average. So 2 minus 1, now you're going to get positive. If the deviations are above the average, 3 minus 1 is 2, they'll be positive. So you'll have negatives and positives. And one thing I want you to notice is that if you add all these up, what do you get? You'll get negative 4 and positive 4. And if you add them together, you'll get 0. Do you think that always happens? Let's see. Let's try it here. So now we'll look at our second step. We'll do the same thing, and we are trying to get the deviations. So what we're doing here, I'm going to label this. This is the deviation step for both of them, the deviations. So now what do we want to do? Here's our list of numbers. We want to subtract 1 from each and every one of them. See, negative 9 minus 1, negative 10. Negative 9 minus 1, negative 10, negative 10, negative 10. All right, what are the next? Now how about these ones? What do you think? They're right at the average. They're going to have 0 deviation from the average. So 1 minus 1 is 0, 1 minus 1 is 0, and 1 minus 1 is 0. How about 11? What's its deviation? 11 minus 1 is 10. It's 10 above, 10 above. And our last one has a deviation of what? What's our last deviation? Last deviation? 20. Thank you. All right. Now, let's see if that happens again. If we add them all up, let's see what happens. We get negative 10, 20, 30, 40. Negative 40. Do we get positive 40 over here? Yes. They sum to 0 again. And that will always happen. If you did your calculations correctly, the deviations will always add up to 0. So it's a good way to check to make sure that you did do your deviations correctly. So let's write that in. So make sure the deviations sum to what? To 0. Now, this is the key to why calculating a standard deviation is so tedious. Because if they didn't sum to 0, we could have just said, let's just take the average deviation, couldn't we? And that would be a really good measure of the standard deviation. But it's always going to be 0 no matter what. So it's not going to tell us anything about how spread out the data is. So you might think that's because the positives and the negatives cancel out. And why we don't really care when we're talking about the typical spread. We should just neglect positive and negatives and just look at the absolute value, the size of the deviations. So if we did that, what would we get here? We'd add all these up and we would forget about the sign, and we get 4, 5, 6, 7, 8. And then we take that average, which would be 0.8. And that's sort of how you should think of the standard deviation, but it's not the way statisticians do it. Simply for the reason that the absolute value function is a very difficult function to work with. It's just, it's not useful. It's really a pain to work with it because it's not an analytic function. It comes to a point, the graph of it. It's not differentiable. It's zero. It's a hard function to work with. So we scrap that, and what statisticians do instead to get rid of these signs is our next step, which is to square each deviation. So that's going to be our next step. But I want you to, when you eyeball it, and you take the deviation, it's just going to be a little bit bigger usually than what you would get if you just did the absolute values first and then took the average of the absolute values. So now we're going to square all these. That's what this says, square the deviations. So we square them. 1, 1, 1, 1, takes away the sign. 0, 0, 0, 1, 1. So far it's just like the absolute value, but this one changes to a 4. And we'll do the same thing here. And we get 100. Negative 10 squared, another 100, another 100, another 100. The zeros stay at 0, 100, 100, and what's the 20 change to? 400. Okay. So now we've got this squared each deviation. Okay, we're here. Now we have to find the average of the squares. So we're at step 4. So we add all these up together, 1, 2, 3, 4, 5, 6, 10, and divide, and we get 1. So I'm going to call it the mean instead of the average, the root, because you'll see another way, what people refer to the standard deviation as the root mean square. And here's the mean, and we'll do it here. We'll call it the mean here too. So this is what? 100, 200, 300, 400, 500, 600, 1,000. Divided by 10, and we get 100. So here we are at the mean. Now, we don't want the mean of the squares. That's going to be too big. I mean, it's not the same units that we started off with. So we want to take the square root to get it back into our original units. So we'll call it the root, the square root. So here we take the square root, and it's 1. And here we take the square root, and it's 10. So what did we get? If we'd taken the absolute value, we would have gotten 0.8 here. If we'd taken the absolute value here, what would we have gotten? Let's think about it. We would have had 10, 20, 30, 40, 50, 60, 70, 80. 80 divided by 10, the average of the, so we would have gotten 8. So usually what happens is it's just a little bit bigger when you do it this way than what you would get if you'd taken the absolute value. But the way you should think about it is to remember it, and a lot of people call it this, the root mean square, because you start here, it's the root, the square root of the mean of the squares of the deviations from the average. The root mean square, which you'll see a lot in statistics. Now I know we only have 5 left, but we just have to, I just want you to think about the same thing we thought about before, how with average and median, how is the standard deviation now affected if you add a constant to all the numbers? We saw the shape didn't change. And how would the standard deviation be affected if you multiplied all the numbers on a list by something? So find the standard deviation. Why don't I tell you that it's 2, and I want you to see if you can do the work to get there. Now, subtract 3 from each number on this list. This is just a thing, I mean, you don't have to do any calculation. Imagine, you subtracted 3, so the numbers would just go down by 3, right? Just go down by 3. Do you think the spread of the numbers would change? Do you think the standard deviation would change at all? No, wouldn't you have the same spread, the same shape? So if you subtracted 3, I'm just going to say, what is the new standard deviation? It would be this, it would not change. Why? We can fill this in more later and do the calculation, because the shape, the spread of the histogram would be the same. The spread would not change. It would just shift. So the SD would still be 2. It's just going to shift it down, just like when I showed you that graph with our exam scores. Imagine just taking the same histogram and shifting it. But now, what if you doubled every number on the original list? If you doubled every number, just watch. Here's your original list. This will just take me a moment. And now you double it. This is the original. Well, what happens? This 0 would stay at what? Times 2 is 0. 1 would double to 2. 2 would double to 4. 3 would double to 6. 4 would double to 8. 5 would double to 10. And 6 would double to 12. And look at the spread. What do you think would happen to the spread? It would double. So what is the new standard deviation? The SD would double. The histogram would get stretched out by a factor of 2. The histogram and the spread of the numbers would get the histogram would stretch out. Now, before you pack up, I just want to make sure that everybody understands, okay, next time we're going to cover the normal curve, and I'm going to try to get you ready for the exam. Next time is a very important lecture. And so thanks a lot for participating, and see you Thursday.